The evolution of graphics APIs. Graphics APIs have been the unsung heroes of the kernel wars, serving as the critical bridge between surfacing algorithms and visual output. These interfaces translated mathematical constructs like Bézier surfaces and NURBS into renderable forms, powering CAD, visual effects, and scientific visualization. The evolution of graphics APIs reflects a fierce battle among industry giants IBM, HP Labs, Sun Microsystems, and Silicon Graphics, SGI, each vying to define the standard for 3D rendering. This chapter explores how APIs shaped surfacing technologies, from early standards like FIGS to OpenGL's dominance and the rise of modern low-level APIs, while highlighting the vendor rivalries that drove innovation. Graphics API Library Timeline. Graphics API Library Timeline. Early standards, GKS, FIGS, and GRAFIGS. The roots of graphics APIs trace back to the 1970s with the Graphical Kernel System, GKS, an ISO standard for 2D graphics adopted by IBM and HP for early CAD systems. GKS provided a device-independent framework but lacked robust 3D capabilities, limiting its use for complex surfacing. By the 1980s, FIGS, Programmer's Hierarchical Interactive Graphics System, emerged as a 3D successor, offering a hierarchical structure for managing complex models. IBM's GRAFIGS, a high-performance implementation of FIGS, ran on mainframes like the IBM 3090 and Unix workstations, supporting Bézier and NURBS surfaces in early CATIA and CDRS workflows. GRAFIGS was optimized for CAD but suffered from rigidity and slow performance in real-time applications, making it less suited for emerging VFX needs. IBM pushed GRAFIGS aggressively, leveraging its mainframe dominance to integrate it into engineering workflows at companies like Boeing. Meanwhile, HP Labs developed its own FIGS-based solutions for the HP 9000 series, focusing on scientific visualization for oil and gas industries. Sun Microsystems, a rising Unix workstation vendor, adopted FIGS for its SPARC stations but prioritized portability over performance, lagging behind IBM's optimized implementations. SGI, however, took a different path with its proprietary IRIS-GL, introduced in 1983 for IRIS workstations. IRIS-GL's hardware-accelerated rendering of NURBS surfaces, used in Alias/1, gave SGI an edge in automotive and VFX markets, setting the stage for a fierce API standards war. The rise of OpenGL and vendor rivalries. In 1992, SGI transformed the landscape by releasing OpenGL, a cross-platform API derived from IRIS-GL. OpenGL's flexibility, hardware acceleration, and vendor-neutral governance under the OpenGL Architecture Review Board (ARB) made it the de facto standard for CAD, VFX, and games. Supporting Alias/1, Maya, and ICEM-Surf, OpenGL enabled precise rendering of NURBS surfaces on diverse platforms, from SGI's Onyx to HP's Visualize workstations. Its open nature outpaced proprietary APIs like GRAFIGS, which IBM struggled to adapt to commodity hardware. The 1980s and 1990s saw intense competition. IBM, banking on GRAFIGS, invested heavily in its RS/6000 workstations, targeting aerospace and automotive CAD. HP Labs countered with Starbase, a proprietary API for HP 9000 systems, optimized for scientific visualization but less versatile than OpenGL. Sun's XGL, introduced in 1993, aimed to compete with OpenGL but was tied to Sun's SPARC hardware, limiting adoption. SGI's dominance in high-end graphics, fueled by OpenGL and its geometry engine, made it the preferred platform for Hollywood VFX, /Jurassic Park / 1993, and automotive design, Ford Taurus. However, SGI's reliance on proprietary hardware left it vulnerable as NVIDIA's GPUs and OpenGL's portability shifted the market to PCs. The 2009 release of OpenGL 3.2 introduced the core profile, removing deprecated features and optimizing for modern GPUs like NVIDIA's GeForce series. This update enhanced complex surface rendering for ICEM-Surf and CATIA on commodity hardware, further eroding the need for specialized workstations. OpenGL's cross-platform support also enabled Maya to run on Windows and Linux, democratizing access to high-quality surfacing. Successors and modern APIs. By the 2010s, OpenGL faced challenges from Microsoft's Direct3D, which dominated PC gaming with DirectX 9-11. Direct3D's tight integration with Windows and support for NURBS tessellation in DirectX 11, 2010, made it a viable alternative for CAD and VFX. Apple's Metal API, 2014, designed for macOS and iOS, optimized GPU performance for surfacing in tools like Autodesk Flame, though its platform exclusivity limited adoption. The Kronos Group's Vulkan, 2016, addressed OpenGL's inefficiencies, offering low-level GPU access for real-time surfacing. Vulkan's efficiency powers Unreal Engine 6's holographic NURBS, enabling AR/VR design for Meta's Horizon worlds. WebGL, 2011, based on OpenGL, brought surfacing to browsers, enabling cloud-based CAD platforms like Onshape. WebGPU, 2023, a successor to WebGL, further enhanced browser-based rendering, supporting AI-driven surfacing for medical visualization. These modern APIs integrate with Neural NURBS and Adaptive Mesh Refinement, AMR, enhancing Hollywood VFX, Tomb Raider 2 ***, 2025, and real-time surgical simulations. However, the shift to low-level APIs like Vulkan and DirectX 12, 2015, has increased developer complexity, sparking debates over accessibility versus performance. Vendor battles and industry impact. The API wars were as much about vendor strategy as technology. IBM's graphics faltered as its RS/6000 line lost ground to PCs, and by the late 1990s, IBM shifted focus to software like Kedia. HP's Starbase faded as OpenGL became ubiquitous, though HP's workstations adopted OpenGL for CAD. Sun's XGL and SunGL, a partial OpenGL implementation, failed to gain traction, contributing to Sun's decline before its 2010 acquisition by Oracle. As we mentioned before, SGI's OpenGL success was bittersweet. While it standardized 3D graphics, NVIDIA's CUDA and commodity GPUs rendered SGI's hardware obsolete, leading to its 2006 bankruptcy. Graphics APIs have been pivotal in surfacing's evolution. FIGS and graphics enabled early CAD, OpenGL democratized high-quality rendering, and Vulkan and WebGPU support cutting-edge applications. These APIs have shaped industries by enabling precise, real-time visualization, from automotive Class A surfacing to medical imaging, while vendor rivalries drove innovation and disruption.